have here the overview. So starting on the condenser, we have here certain vacuum inside. We're getting condensate out here with a pump into the boiler. The boiler will produce our steam either with a heat source, a fire, coal burning, etc., or with the exhaust gases from our turbine. We will create here a certain pressure and temperature from the steam, and this steam is sending onto our turbine, and from the turbine, in the easiest case, let's say it's getting back into the condenser. Condenser, we're condensating the steam again and sending it back into the circle. For the condensation over here, it can be that we have, like in this case, cooling tower in, fresh water, air cooling, etc. There are many cases. We saw we need to get certain heat away. So this is a couple of megawatts thermical, which we need to compensate somehow. And then we have the normal process. So in this process, it's an one pressure process. Yeah. So what's missing here is, for example, the LP pressure. The turbine is connected to the generator, and the generator then, let's say, the electrical output is what's bringing us the benefit. Yeah. So that's where we getting the earnings for the power plant. Yeah, so we're selling the electricity, and that's our income here coming in. And of course, we need to pay over here for the heating. Yeah, so either the gas for the gas turbine, the coal for the boiler. Yeah. This is all what we need to pay for. We have here on the cooling water side normally some regulations and some limitations in, depending on if you're using seawater, if you're using river water, if you're using cooling tower, yeah, then you have limitations in. For the operation medium, of course, we using the purest, so demineralized water without any salt and gases in there. Yeah, so that's our medium, which is of course again expensive to produce. That's why we want to save as much as possible out of it. That we not don't need to reproduce this water a lot. So that should be a closed circle. And in this example, there is another case in which I think an IREC is not really there. Yeah, this is here is the district heating. In Europe, it's common. In Korea, we have it. Yeah, so it's normally that we're using heat or that we're taking an amount of steam out of the steam turbine and bringing it into an heat exchanger. So our electrical output will be reduced. So we're taking here an amount of steam out of the steam turbine, getting it over an heat exchanger, increasing the medium here from the district heating. So this is over here, sadly in German in there, but this one over here is district heating. So you have a return line which coming back with a colder temperature, and you're sending it back over here with a hotter temperature. And what we're doing is we're taking steam out of the turbine, increasing here the water temperature from the district heating system, and sending it to industry, sending it to households in the city. So, for example, in Berlin, so capital of Germany, they have a lot of district heating. So that meaning the household don't need their own heater. They have a central heating system from the city. So the power plant is producing the heat, sending it into the heating system. And when they now winter is coming in Germany, yeah. So when it's getting cold and they open up their heaters, then they taking the heat over here from the district heating system. Advantages for the households is, of course, they saving a lot of cost. They don't need an own heater system, let's say gas, coal, whatever you can use here to produce heat over there. So they're getting it from the power plant directly. There's a full big city grid over there for district heating. Big advantage for them, yeah. Advantage for the power plant is that the prices for district heating are normally pretty stable, yeah. So comparing to electrical prices where you have a lot of influence, at least in Europe at the moment, yeah. So there are a lot of influences in, and the price sometimes skyrocketing high and then it's low again, and it's not easy for the power plant owners, let's say, to run their and making their benefits. The same time, when you have high gas prices, high oil prices, yeah, then your benefit will get lower and lower. And with the district heating, the prices are more or less stable or can get increased, and you're losing a little bit from the electrical part because you're taking steam out, but can then send here megawatt thermical, yeah, which you don't need to send through the condenser then. So overall, the efficiency from the overall power plant is increasing. And this can go up to 80, 90% when you're seeing it with the amount you're getting in and what you're getting out. So it's for the power plant owner, it's highly beneficial. And let's say district heating at night will be always used, yeah, even in summertime, some parts using it, yeah. And this is a solid basement over here. In IREG, I think it's not there, so it's just in here for information. And on the next page, we see then also why we can, or what's the increase when we're doing it. Yeah, so we have here the Sankey diagram for combined cycle. So over here, we have our fuel amount. In this example, it's for 680 megawatt, so 100% fuel. So it's an baseload unit with 685 megawatt. So combined cycle, gas turbine probably with 420 megawatt, and then a steam turbine with 260 megawatt, something like this. And together for 685 megawatt. To reach this amount, we have an 100% fuel in here, 100% fuel amount getting in. So that's what we're paying. And from these gas we're burning, and the gas turbine efficiency is normally round about these 40%. Yeah, so 40% we're using for the gas turbine, and this is getting then to the GT generator and coming out. Yeah, 60% is our exhaust gas, which we're sending to the boiler. For the turbine itself, then, let's say the turbine is producing here 80% of the power. So let's say 80% will be produced here, 40% will be used for the compressor, so 40% is coming out at the end. So our turbine, when you say it in a different way, let's say when your turbine generator on a gas turbine, we say over here on the downer side, and you say your turbine in this case is probably making a torque over here from 400 megawatt. So that's the amount on the generator, let's say, which you are generating and sending into the grid. Then the turbine part of the gas turbine would produce 800 megawatt, so the double amount, and the compressor will use 400 megawatt just to compress the air. So half of the power from the turbine, what the turbine is producing is getting into the compressor, and the other half is what we really see on the generator. So that's what this one should tell us. So the turbine itself is producing, let's say, normally double the power you're seeing on the generator outlet. Because you need a really massive amount of power to run the compressor. And that's what is showing in here, yeah. So for the water steam circle, this is coming all here on the left side. But for the gas turbine over here, so this is really turbine, meaning GT, yeah? Not steam turbine. So gas turbine, the turbine would produce 800 megawatt over here, 40% or half of it going to the generator, half of it going for the compressor so that the compressor keeps running. And then we have some small losses over here. Yeah? Gas turbine, yeah, compressor, you see the amount of power you're using here. It's pretty difficult for the big turbines, let's say, when you want to make this external, yeah, when you say, hey, I have an high efficiency compressor, which is probably just using 300 megawatt, yeah, and can do the same amount of compression there, the same air amount, and so on. For the gas turbine, the goal is always to keep it internal, yeah, because an external system could fail, and then you're running your turbine without compressor, and this will lead to a lot of damages on the turbine because you have also cooling lines in there, cooling the blades, etc. So you want to keep it internal, and of course the engineers trying to increase here the efficiency. So when this amount is going lower, so when the compressor over here would be just using 350 megawatt, probably in a different color, let's say, would use here 350 megawatt. That would mean when the turbine part is still producing 800, you will get here 450 megawatt more output. And that's of course the goal where they're trying to get, yeah, that they're getting a higher power output over here. With the higher output, your efficiency would increase, and therefore the overall efficiency of the power plant would increase. So that's for the gas turbine side here, yeah. So gas turbine side, we are somewhere around these 40%. Probably 41 on the newer ones, 42, but let's say roughly on these 40%. Then we have this big part over here, exhaust gas, 60%, where we, let's say, is normally the losing part, yeah, the exhaust gas, which we sending now into the boiler. Inside the boiler, we producing our steam. We producing our preheating water, etc. And then the steam will get onto the steam turbine, yeah, and the steam turbine has normally an efficiency here, let's say 20%, which will come out. One question in between. Can you check, please, if Saba is now working and if you can download the presentation? Because it should work now, and before, I think I was asking before the last break already, and could you please check if you can access Saba and can reach the document or can download the document?
We will check now, Mr. Sebastian.
Yes, thank you. Because otherwise the admin probably need to check again, yeah. But they saying now it should work. take your time and try if you can download it.
Okay, we will try that, and you
Yeah.
can continue. Yeah,
Okay. Okay. Just give me a feedback, please. Yeah. When it's not working.
Okay.
Okay. So we have here from these 60%, let's say 20% is later on the electrical output or the torque to the steam turbine generator. So that's roughly then together with the GT generator, these 60% efficiency what you can reach. Let's say efficiency 60%, which is normally always the common cycle goal. The new power plants now, let's say they are somewhere at around about 63 to 64% overall efficiency. So that's with increasings mainly on the gas turbine side here. What I said, they're probably 42, 43% over here, and then here probably to 21%. And then you're getting to 63, 64% overall efficiency from the combined cycle. Yeah, and there, this is the, let's say the goal at the moment. Of course, the higher the efficiency, the more electricity you're getting for the gas or oil you're paying, and this is of course the goal. So 20% here to steam turbines, 40% to the GT generator, and then we have still here, let's say 40%, which are at the moment not used. There is 1%, which we had over here. So in general, 1% is heat losses, water losses, losses from auxiliary systems, etc. So this is just, in summary, around about 1%. So this one, of course, trying also to reduce it as much as possible. Yeah, that there are heat losses, limitation, yeah, best efficiency over there to reduce this one. And then there is one really massive part, which is, let's say, the biggest part over here. This is the 31%. This is the condensing energy. So 31% over here, let's say, is what we condensing in the condenser. So when we say 31% of 685 megawatt, there we are somewhere over 200 megawatt, yeah, or 220 megawatt even, yeah, which we are not using. So this amount is just, let's say, for heating cooling water. So that is condensation process, and this will be, let's say, lost or not lost, probably not usable. Let's say it like this. So at the moment, let's say you cannot use, or you're not using it in a normal power plant. So the water will be, the cooling water will be heated up, and the condensation process is happening, and then the cooling water increasing the temperature, and this cooling water is then getting back, or you sending it to the air with the cooling tower, etc. But this is not used at the moment in most power plants. So these are these 31% over here. And then we have another part in here, the 8%. So 8% over here, that's exhaust gas temperature. Exhaust gas temperature is an chapter, let's say, for its own. There are different values in which are influencing the exhaust gas temperature. So one time it's the saturating temperature. 。    。  Let's make it in red. saturation temperature from the NOx, so our NOx exhaust gas inside the exhaust gas, you have a certain saturating temperature. And when you get below this saturating temperature, the NOx gases which are inside the exhaust gas will be condensing on the boiler piping from inside the exhaust gas side, let's say. So from the outside of the piping. They will stick on there, they will lead to corrosion on the piping, they will damage the piping, and so we want to stay with the exhaust gas temperature above the saturation temperature from the NOx gases. So this is normally, I would say, somewhere above 55 degrees or something. Somewhere in this area. Second point is sometimes that you have government regulations in there, so that they're saying here you are allowed only to go to 80 degrees or whatever, yeah. That's what you are allowed to. And this is, of course, then also the second big part where you have losses in these overall diagram, so in the Sankey diagram. So you have here 39% with the 1% from the auxiliaries, 40% losses in here. And this, of course, you try to reduce as much as possible. So we saw already here gas turbine will increase, yeah, steam turbine somehow getting a little bit more efficiency so that we're getting here to 63, 64%. And then what we can also do, and that's where the district heating is coming in again. So I would just draw it in. So when we say we have here one part which is going to district heating. So we're taking steam out from the turbine and it's going into the district heating system, and then the district heating system taking a certain amount of water or steam away. So our amount to the condenser is getting reduced. So probably steam turbine will just go to 18%. Let's say it like this for the moment. Here all away that it's getting more clear. So probably steam turbine is getting a little bit reduced because you're taking steam out of the system. So your electrical output over here on the generator side will get reduced. But on the same moment, let's say you're bringing a lot of condensing energy, which will normally getting here to the condenser, there will be a part getting to the district heating system. So let's say we have here something like 20%. So when we take it now together, we have 40% over here, we have 18%, we have 20, so it's 58, it's 78% overall efficiency what we're taking, and we're reducing here this one 78, 86 probably to 14%. So we're reducing our condensing energy, so the energy we throwing away, yeah, and therefore increasing our overall efficiency. So from 100% fuel which we are paying, we're using now probably 78% instead of 60, 62%, yeah, or on an older power plant, probably 55%, yeah. So that could be a way to increase over here, let's say, the efficiency by reducing the condensing energy, and probably in future somehow we'll find a way to use the heat which is still here, probably sending it through something else where we can get it, or using the condensing energy for heating up water, which we then can send, or there are still possibilities, yeah. The difficulty is to find something which is from the price-wise so efficient that we can say, okay, it's efficient and it's not too expensive, because it's not helping when I need to build here a district heating system in Iraq, yeah, and say here I need to build a whole district heating system, which is costing hundreds of millions of dollars, yeah, and to say, oh, then my power plant is over here 10% more efficient and I'm saving, I don't know, $100,000 a year. Something like this is, of course, in relation not possible, yeah. But when district heating system is there, it's always a way, let's say, to increase the overall efficiency. So that's just for general overview over here. And then when we go to the process now again, so this is Clausius-Rankine process. So that's what we had before already in a short way. Yeah? So we're starting again over here with the overview. So that's the overview. We have our condenser, we have the pumps in, we have the steam generator in, we're getting the hot exhaust gases in, and we have our steam turbine in with the coupled generator. From there back to the condenser. So that's our left side, yeah. So that's our process picture over here. And on the right side, we have the TS, so temperature entropy diagram, what I showed before already, where I showed that the evaporation process is happening at the same temperature, and also condensation is happening at the same temperature. And here we can then read out, let's say, the energy we getting in here. So when we're starting here from the outlet of the condenser, so the condenser condensed our steam already, and we're saying here we're starting over here. So normally with the CEP pumps, yeah, condensate extraction pumps, we're getting here through. Condensate extraction pumps are increasing our pressure in the system. The pressure in the system, which you can see here on the TS diagram, with this step from 1 to 2. So it's here the increase in the pressure. And when I go back to this diagram, just to show you, you can see here, when I make it a little bit bigger, because otherwise you cannot see it, you can see here the curves with the increased pressure. So here on top, yeah, 10 bar, 20 bar, 50, 100 bar, and they all getting down here. So that's the increase of the pressure, which going here next to it. And that's our first step in the process. So that's increasing of the pressure. So second step, which is all happen then in the steam generator. So it's one time the preheating, so condensate in here up to the vaporizing temperature, or steaming temperature. We have the evaporation in, which is happen at the same temperature, and we have the superheating in. All this happening after normally the feed water pumps. Yeah, here is just the pumps in, then getting into the steam generator, and in the steam generator first in the economizer preheating happening, then the water is getting into the drum. From the drum, it's getting into the evaporator, back into the drum for separation, and then going further into the superheater for superheating. So these 3 steps are happening within the boiler. Preheating, evaporation, superheating. Preheating, 100% water. Evaporation, on the inlet, 100% water. On the outlet, 100% steam. Superheating, only steam. So from there, outlet of the boiler, we getting into the steam turbine, and on the steam turbine, we have an expansion in. So the expansion going through the different stages of the turbine. So what's happening? My pressure is getting reduced, my temperature getting reduced, the steam is getting expanded, and we transferring the energy from the steam onto the generator. So into, no, not onto the generator, into rotating energy onto the blade, onto the rotor, and then transferring it with the rotor, the rotating energy, into the generator. And inside the generator, we're producing then electrical energy, and this electrical energy will be sent to the grid then. For the turbine, we're getting in here with a high temperature, high pressure, and then getting, in this example, one pressure stage getting through the turbine until we get from the turbine outlet, getting turbine outlet into the condenser, and inside the condenser then have the condensation process, same temperature of steam temperature and condensate temperature, and then the condensation process happening over here, condensation happening, our heat from the condenser is transferred onto the cooling water, and then we coming back here to 100% condensate and getting back to the pumps, and the circle is running again. So that's the Clausius-Rankine process. Yeah, so that's what's going on. Pressure increasing, preheating, evaporation, superheating. So that's the general Clausius-Rankine process over here. And that's what happened in your power plant. In your power plant, then also, let's say you have the HP circle, you have an LP circle in. So LP is the same happening with preheating, evaporation, superheating, and then getting into the LP turbine. Over here, we see now the Clausius-Rankine process with the reheating in. So as said before already, it can be that we have reheating in. Your turbine don't have it. You have HP and LP, but you can have an reheat in, and then the process, of course, is also working. So first of all, when we go one step further, so that was our condensation. We are now on the same point like before. So turbine overview. Here is our boiler. Sadly, it's not in English. Yeah, so this is the boiler, preheater, evaporator, superheater. Getting here onto the HP turbine. From the HP turbine, the steam will be sent back to the boiler. We have an intermittent heating, yeah, heating over here, yeah. So the reheating, so that's the word, yeah. Reheating over here. So the steam which coming out here, probably 300, 350 degrees, will be sent back to the boiler at around about 30, 35 bar normally. Sent back to the boiler, will be reheated again to 550, 600 degrees, what we have, and then sent back to the turbine, and then sent through the LP turbine, and then same like before through the condenser and down. Yeah. So on the downer part here, we are on the condenser. So the condenser is our first point. Second step is now we have the feed water pumps or condensate extraction pumps, and then the feed water pumps to increase the system pressure. That's our one-time system pressure increasing. The next step is then to get the preheating or economizer through the economizer. So there our temperature will be increased. We're getting up here to the point 100% water, but near saturating temperature. For this pressure we have inside the system, and the pressure is set up here by the pumps. So over here then, certain saturating temperature over here after the preheating. Then we have the evaporation in here. So the evaporation is happening. We're getting here now, after the evaporator, 100% steam with saturating temperature. And afterwards, we're going through the superheater. The superheater is heating up until we're getting to our maximum temperature, which is designed, let's say, one time by the boiler, and one time, of course, also what the steam turbine can handle. From there, we have the expansion through the HP turbine. So we're getting through the HP turbine, our steam temperature will decrease to a certain value. We set TM over here, so probably 300, 350 degrees. And we're sending the steam back into the boiler. So we're getting here a certain amount of reheating. The reheating has happened to the maximum temperature. In some power plants, I already saw it that the temperature is even higher than on the HP part, because that's depending on the steam turbine. On the HP part, you have the high pressure and the high temperature. So stress for the material is one time the stress coming from the high pressure, and one time the stress coming from the high temperature. So these two together defining our stress over here. So when you have then a reheating in, and you have here a certain temperature, it can be that the temperature can go a little bit higher, because the material can probably handle 10, 20 degrees more, because our pressure is reduced. So on HP part, when we say we are here at 100 or 150 bar, yeah, on the IP part, we're probably at 30, 35 bar. So the pressure is extremely reduced, and therefore the temperature is not as critical as it is on the HP one. So it can be the temperature over here is the same, it can be getting even higher. So and then we're getting through this turbine, it's called here an LP turbine, yeah, it can be an IP LP turbine combined one, it can be an IP LP turbine separate one, but for the process here it's let's say one turbine. So we're getting in here with the hot reheated steam and have the expansion now through these turbine parts, through the stages, and getting there now to the outlet of the turbine over here. So the turbine outlet part, where we are somewhere in the vacuum area, and from there we getting into the condenser, getting through the condenser, condensation process of the steam is happening, same temperature, and we are getting back where we started, let's say from here 4 to 5 through the condenser, and we get here our condensate back and the outlet of the condenser. So the main purpose of the steam reheat is to increase the steam fraction of the wet steam after expansion in the turbine in order to prevent erosion of the blades in the final turbine stages due to the moisture content in the steam. So that's what we had before. When I go back to the other diagram over here, we saw over here in this diagram, we have a certain amount here of wet steam. When we're getting here from high temperature to the lower pressure and we're getting into this wet steam area, this of course we want to avoid. So we superheating it again and moving our X value out so that there are less water content inside the turbine. Yeah, so otherwise you would go down, getting into the wet steam area. So we increasing the temperature again, getting here on the outer side to stay out of the wet steam part as much as possible, so that only probably the last stage of the turbine is seeing a higher amount of water. And this one we can prevent then, yeah, can protect the turbine by a certain coating on it to make sure that the steam turbine is able, or the blades are able to handle this temperature. And the turbine is subdivided here in the high pressure and the low pressure section. Yeah, so this is HP and LP turbine, which we saw before. So we have here one time, that's what I said, is over here. This is HP turbine, and over here is LP turbine. This one is the superheater, just to make it sure for you. This one is the boiler. And then we have here the reheater, and this one is the pumps, and over here the condenser. So that's to make sure. And then we have over here in a reheater the steam that has been expanded in the HP turbine is heated to roughly the same temperature as that of the main steam. The thermal efficiency can be increased if the average temperature of the heat input for the cycle process is higher than that of the cycle process without reheat. So we have here the temperature, and then we have here the reheat, and we're increasing the temperature, so the efficiency from the overall cycle process will be increased. That's why we see in most cases, let's say that we have a reheater in there for the modern ones, that we have the 3 pressure stages over there. In Siemens, we already had one with even 4 pressure stages, to increase the efficiency and, let's say, to take the biggest amount of heat out of the overall circle over here. Okay, so that's to this one. I hope that is clear so far for you. And then we have now, let's say, more or less the basics, so the introduction with the basic processes we have behind us now. And then we getting into the systems. Are there any questions from your side before? Or so far everything clear? Okay. Then we going on, and we go on, of course, with the BOP system. So your systems you have in your water steam circle, and therefore starting with the condensate water system, because this is the first system you have in there. And for the condensate system, we have over here the overview. One time, let's say we have here our condenser. Condenser is clear, I think, so far. We have here on the downer side then the connections to the CEP condensate extraction pumps. So there are the 3 condensate extraction pumps, yeah, LCB 30, AP01, 001, LCB 20, and LCB 30, AP001. And the pumps, of course, what you can see here then already, they have an min flow line, which are going back to the condenser. You have then the outlet valve, yeah, outlet valve when the pump is running. Red is running for you, yeah. Just so red is open, yeah. So red pump is running, so you're getting here your certain pressure in the system. We have here on the right side the dam and water connection, yeah. So this is coming from dam and water pumps, dam and water tank, and therefore getting one time into the system connection over here so that you can fill up your dam and water system after an outage, for example, or keeping it under pressure during that's the reason. Saif? Was it a question or anything else?
No, thank you. No, thank you. Can't.
Okay. So dam and water connection over here. Dam and water connection is going one time to the vacuum system. So our evacuation pumps, yeah, which creating the vacuum for the condenser and removing non-condensable gases over here. We have a connection to the CCCW system, so closed cooling water system, yeah. Closed cycle cooling water system, it's called here, yeah. So there is also dam and water getting in to filling up the system, increasing the system pressure over here. And then dam and water is also going up here to these 2 LCP-AA003 and LCP-10-AA101. So these 2 wells, they are controlling, they are for the makeup water and controlling, let's say, the level in the condenser. So the goal is always, let's say, to have a stable level inside the condenser. So that's what we're controlling. When you would increase the flow to the boiler, so you're increasing your load, so you can produce more steam in the boiler, more steam will get through the steam turbine. So in the condenser, the level will go down. So you need to refill it, yeah. And the other way around, let's say when the load is getting down, so the flow in the boiler will be reduced. The condenser level would increase, and then you need to remove water out of the system by the drums or other system where you can reduce water out of the system, or where you can drain water out of the system. So that's a condenser over here. We have then here downer side our extraction line. We're getting here the line to the spray water for the external flash tank and the internal flash tank. Yeah, so that's where steam getting in, and then let's say the steam from the drain lines, yeah, or probably condensate from the drain lines, and it can be that it's steaming out. So we're spraying the water in the flash box to make sure that the steam is cooled down before it's getting into the condenser. We have then over here the MinFlow line for the condensate extraction pumps. So these are LCE 13 AA101, LCA 32 AA101. So these are controlled lines for the MinFlow. But as soon here, let's say the outlet would be open, you have a certain flow here to the outside to the two boilers, then these lines will be, of course, closed, and they will just open up again when there's no flow at all anymore. Over here, there are then the lines for our HP bypass station or desuperheating and depressurizing stations, yeah, bypass stations. So therefore, we need to spray water in, because when the high pressure steam will be sent directly on the condenser, that would be not ending good for the condenser. So you need to reduce the pressure, need to reduce the temperature before. With the HP bypass stations, then you're spraying water in, condensate in to reduce the temperature over there. Pressure reduction will happen in the pressure reduction part of the bypass valve over there. So these are, let's say, suppliers which will be fed also by the LCB pump. And then from here, we going to one time the bypass gland steam condenser. So that's our bypass when the gland steam condenser is not in operation. And we have over here then the gland steam condenser. So gland steam condenser is where, say, the gland steam, the leak steam from the steam turbine will be collected. It will be condensed here. So the heat which will set free, let's say, is used to warm up the condensate. This is a measurement in here which can increase the overall efficiency, because when you're getting here something similar to a preheater, yeah, you're not wasting the heat energy you have there, you're using it to warm up your condensate over here. The amount is in most cases, I would say, not enough to increase the full volume of for full condensate volume over here. Yeah, so there's a regulation valve, and they will control a certain temperature here on the outlet, and a certain amount will go through the gland steam condenser, and another amount is getting here through the valve. Yeah. So from there, getting over here, so here the MinFlow line again, and then we have here the LP heater. So the LP heater is a preheater here for warming up it's like a preheater, let's say. You have a bypass for it when there's in any case problem here with the LP heater, and from there getting one time over here to the sampling system, boiler 11, boiler number 12, and to the BD tank. LP heater drain line, yeah, getting back in here into the system, not leaking this out, yeah, or sending it somewhere else. So that's the overview from the condensate system, just with the HMI. And when you see now function-wise, yeah, so this is the function description, yeah. First of all, of course, extraction of condensate out of the condenser hot well. That's the main purpose, sending the condensate via the condensate extraction pumps through the Gland steam condenser, through the LP heater to the boiler systems. And then also forwarding condensate to the seawater system, external and internal flash box, so the ED and PD flash boxen or tanks, yeah. HP steam bypass station desuperheater, LP heater system, Gland steam unit desuperheating water, and condenser water, certain spray water, cooling the Gland steam condenser, so condensating process inside the Gland steam condenser, because the Gland steam is of course steam again, yeah. So there will be condensation happen over here. Condensate extraction pump min flow is discharged back to the condenser. That's also what we saw. That's the min flow line. That's opening as soon there is no consumer in the system, or when you're starting up the system will be start running, condensate pumps will increase the pressure in the system, and then you need a certain min flow before the systems afterwards are starting up, yeah, so feed water system, etc., starting up. Heating of condensate by ST extraction steam at the LP heater for GT fuel oil operation, and 2 out of 3 condensate extraction pumps. Yeah, each one is around about 60%. So normally 2 pumps are running, 1 is in standby, and this is the normal concept then for the condensate extraction pumps. Critical process parameter we have in here, filling and venting of the system before start of the pump. When we go back here, we saw filling of the system is happening over here with the Daemon water. When the system is completely empty, there will be, with the makeup water, the condenser filled, and then there will be also the condensate system filled up to a certain amount, and there are manual venting lines in to make sure that we're not getting air somewhere into a pump, which can lead then to cavitation, etc. We have then process, of course, condenser level low for the CP NPSH. So NPSH, I said it before already. So this is our net positive suction head. So that's meaning you need a certain suction side pressure for the start of the CP pumps. So that meaning you have a certain condenser level in, because when we draw it in here, you have the condenser somewhere in. You have then here on the downer side somehow the connection pipe, and here somewhere there are the CP pumps sitting, yeah, and the CP pumps make sure that they're going down, and you have a certain pressure, pre-pressure from the, let's say here, from the level from the condenser to the suction side of the pump. So there's a certain level in which you need to have to get the right suction side pressure for the CP pump. That's also a criteria for the condensate extraction pump, so that the pump is not started before the level is there, when you have not the right amount of pressure over there, it can lead to cavitation, and cavitation, of course, can lead to big problems on the impeller over here, and therefore we have these critical process in protections inside the system so that you as an operator are not able to start the pump without the certain NPSH over here. So this is an important part. And then we have the conductivity by circulating water leak at the condenser. Is there a limit for NPSH that we can operate a pump? Yes. The value I cannot tell you. I mean, I can check if there's something in the documentation, but there is for sure for the pump here, when you go into the logic, there's an NPSH value in where the pump getting is operation ready or enable operation. Yeah. Let me check if I find a value. If there is something written on in the PNID. So you have the, when we check over here, so that's the PNID. Sometimes it's written on over here. It's not written on there. So there is no. Just need to check if there's somewhere the value in start permission. This is for the common part. There should be. There is for sure somewhere in the documentation the value in. I cannot see it right now, but you have for sure the value in here for the pump to start. Either it's combined, let's say, with the level, so that they're just saying here the level needs to be higher than, I don't know, 300 millimeters or something. Yeah. This is the normal way, I would say, that you have here certain level in, and then you're saying with a certain level and the geodetical height, you have the certain suction side pressure here on the pump. In other cases, when you have, let's say, the point, then you have it on the pump directly for the feed water pumps normally. But in most cases, I would say that you have it with the condenser level in. So it should be from the protection here, from the levels, it should go to the enable operation of the pump, and the enable operation will just be coming when there is a certain level inside the condenser. This is the normal behavior over here, so that you have there the suction pressure for the pump, in this case, over the hot well level or condenser level. Is this understand from your side? So the limit, I don't know, meeting guest, yeah. So the limit is for sure integrated here with the level. So you have a certain level normally for the operation. I will just check if I find it, if it's in. It must be in the can be in, wait a second. Condensate water level is 58. Condensate water level.
Sir, can you hear me?
Yes, I can hear you.
Sir, before a few days, we have a condition that the level reached to 272 and the pump still in operation.
Yeah, but there should be a min level in, and I'm just checking if I find something, because there is for sure an protection in for the pump. The same like you have for example, for the dam and water pumps, yeah, you need a certain level inside the dam and tank. So you're getting there and warning, level is low, and then you get a protection that the level is too low. Yeah. So this is here, you have here also condenser water level L4, L5, L6. So this will be normally low in. Condenser level higher than this one, and LCB pump start. Main pipe pressure low. Command. Water level high, and there should be somewhere water level low. 0.057 meter. So 0.057. So this should be integrated here somewhere. Condensed. No, this is level high. So there should be a level low protection in. This, from my experience, it needs to be in. And I mean, with this system, it must be somewhere in, because when it's not in and the level is low, you will get in trouble with the pumps, because the pumps will not have the certain MPSH. When the MPSH is not there, you're getting a cavitation on the suction side, and cavitation on the suction side you will hear. The pumps will get noisy, and they will destroy more or less your impeller. And that's what we from Siemens for sure want to avoid. But over here, like I said on the beginning, it's an Chinese boiler and water steam system. But when it's not in, I would for sure, let's say, checking it with the system, because there must be something in with level low. This must be in. So when you're getting here a level low from the hot well, at one point there must be a protection for the pumps. maybe it was not low enough yet. Yeah, maybe it must be under 200 millimeters or something. But there is for sure on every, let's say, centrifugal pump, there is a protection in. When this one is not in, then my recommendation is there, let's say it must be for sure integrated. But I guess when we would check the system over here and checking there the protection from the level, it will be in here that the level low at, I don't know, 200, 150 millimeters at one point, that the pump will be tripped out or getting a protection of. This should be in, I can just say should be because I didn't have the logics and can check the logics. This is the only answer I can give. I'm sorry for can be. I mean, I cannot say something. I haven't been on site yet. I don't have the system logic to check it, but I told you, let's say in the morning with the centrifugal pumps, the centrifugal pumps need a certain suction side pressure. And we will come later on, I will show you with cavitation, yeah, why we need this. And so it should be on every pump, let's say centrifugal pump which need the NPSA, there must be a protection for it in for the pump. Otherwise, when the hot well level will go low to 0 or something, you will probably getting damage on the pump. This is what I can say from my side. Yeah, I mean, you saw the manual. I will check there again if I find something, but I think I also don't get all the manuals, yeah, so far. So for me, it's just I can tell you, take a look for the min level from the hot well, yeah, protection for the pump. NPSH is the big word there, yeah, and if it's like this, then check please if it's somewhere in. Exactly, so that's this one, condenser level low for CP NPSH, that needs to be there normally, yeah. So let's say I never been on a site where it's not there, yeah, because it's there for every pump. You have it normally here for the dam and water pump, yeah, tank level. When the level is too low, you're getting the protection. And normally, let me check. I will just check when So normally it should look like this. So this is now, let's say, from Siemens side. So dam and water tank, what I showed you before. So we have the tank and we have then a so-called vessel protection sheet. So that's this one. You have here the measuring point in. So that's the level. You have the function group, water side, yeah, range 0 to 14 meter, redundancy in, and then you have here your dam and water storage tank. And when you check here, 13.2 meters overflow, you get a warning level too high, 12.7 automatic off. We'll make it a little bit bigger. Automatic off filling from water treatment plan. Yeah. So they're sending the protection out and saying here, water treatment plant, the tank is nearly full. So you can stop producing. Then you have the normal tank level. You have at 8 meters an automatic on filling for water treatment plant. You have here 2 meters, higher than 2 meters, the release for the Daemon water pumps. So we say 2 meters we need in this example, yeah. 2 meters we need for the pumps to start. When the pumps are then running and the level is getting below 2 meters, you're getting a warning. And then we have a low value, 0.7, where it's saying alarm, level too low, and it's sending also the protection off to the Daemon water pumps. And something similar to this, I expect normally for the condenser hot well. So you have somewhere a normal level, you have a high level where you're getting a protection for the makeup water lines. You have a level low somewhere where the makeup water lines getting an open signal so that they're filling up water. And then as a last protection, you have normally the level is too low and the CP pumps will trip. As a protection to protect the pump itself. So that's a mechanical protection over there. Yeah? So to protect the pump from mechanical damage, from cavitation. And something like this should be in on every centrifugal pump. And then you see also the level for starting the pump will be even higher. Yeah? So we're not going in Siemens, let's say, to the lowest value, because this is just not needed, I would say. Yeah. And then it should be working like this. So somewhere there should be a protection in. And this is just for the suction side pressure. When there's less than 0.7, then we're getting the critical parts. There could be then cavitation coming, and this we want to avoid. So this is an example, let's say, out of the fundamentals training. And I think there was also for the drums, you have it, yeah, level, pressure, and then normally also for the condenser, yeah. So something like this, I say, should be somewhere in, yeah. So this value should be somewhere in. So that's for the level. Then we have the protection over here, conductivity by circulating water leak at the condenser. So this is when you have the water-cooled condenser and there is a leakage in. So you have the condenser with the cooling water pipes through it, and the cooling water pipes have a leakage. So you're getting cooling water, which is of course pretty dirty water. Yeah, it's not cleaned, it's not demineralized, etc. So this water will get into the condenser. So your conductivity and your samplings will get pretty bad. So then you can directly see there, okay, conductivity is bad. There was something happened, because we don't want to get these bad values into the whole water steam circle, into the boiler, into the turbine, because they leading to corrosion, they leading to problems in the turbine, salt, etc. Everything can come up there. And then, of course, we have conductivity, corrosion by, for example, an air ingress at the condenser. Your condenser is under vacuum. And when there's somewhere a leak, then air is getting into the condenser. Air getting into the condenser is oxygen getting into the condenser. Your oxygen values will increase, and therefore, let's say, the corrosion rate will increase. And this, of course, we want to avoid, and therefore, let's say, these ones will be checked and controlled, and you will get normally the warning then, conductivity high, and then it's written in, yeah, you are allowed to run for a certain time with the steam turbine, and when the conductivity is getting too high, you need for sure to switch off the steam turbine to avoid any damage on the machine. So then one more page before we making a break. So this is what we had before. So condensate water system and main component enable and protection circuit. So condensate extraction pump enable to start. We need to have a certain condenser level, and the condenser level must be higher than min. So this is the overall start allowance for the system. Yeah, so there need to be a certain level inside the condenser. When this level is not there, you are not able to start the condensate extraction pumps. And then we have, let's say, pump protections. Typical, yeah, what we have is normally condenser level min. So that's what we just discussed. Yeah, so this should be in. So when the level is min, to protect the pump, protect the too low NPSH. So therefore, we have the condenser level protection in here. We have the CEP discharge pressure when the discharge pressure is too low. So that's meaning the pump is running, but probably something with the pump is not right. So your discharge pressure is below a certain value. Can be there's something blocked. It can be that your strainer is full and there's not enough flow getting through. Can be that inside the pump is something wrong, that the motor is running too low. A lot of ways, yeah. So the discharge pressure is getting too low, and then from the protection, normally from the pump protection, it will change over to the spare pump, yeah, and switch off this pump. Suction strainer delta P higher than max. So this is what we saw not over here. So you have here in front of the pump, of course, a strainer in, and the strainer is there to make sure that there are no particles getting into the pump. So you have here the strainer. So you are coming here from the condenser, you have the strainer in here, and the strainer has here an delta P measurement, suction discharge side. When the strainer is getting full, the differential pressure will increase, and then you're getting at one point a warning. And then normally you're changing over to another pump, close the inlet, suction side, cleaning up the strainer, etc. And this is, of course, a ventilation line in here, drain line in here, so that you can drain the filter, cleaning up the filter, and then the pump is available again. So delta P higher than max, you're getting protection for the pump. We have the CEP motor winding temperature. So when your motor temperature, winding temperatures are too high, you're also getting protection from the pump before there's any damage happening to the motor. Same for bearing vibration and bearing temperature. That's normally a point when you're saying, okay, something is wrong. Yeah, so we're protecting it before there's a big damage happening and the pump probably, let's say, destroying itself, yeah, with too high vibration and destroying the two other pumps next to it also. Yeah, so switching off, changing to the spare pump, and then the system is working on. Then we have condenser level protection, of course, level too high, also higher than max. Discharge valve open, either on the drum, drain lines, yeah, wherever it is. You want to get water out of the system. And when the level is too low, so that's again condenser level min, the condensate extraction pumps normally trip. I say typical, yeah, they should trip normally, but checking you probably need to do inside the system over here if it's really implemented. So when you get here from the level low, it should go to the protection of the CEP pump. Okay, that's for this part so far. The next one is then the cavitation, but I would say we're making a short break over here. So I would say till 4:15, so 15-minute break over here. And then we go a little bit on with the system, condensate water system, and probably to the next system afterwards.
Okay, okay.
Okay?
Tomorrow we can start in 8 o'clock, not in 10 o'clock morning.
It's not possible from my side because that's 6 o'clock in Germany and 6 o'clock I'm not allowed.
6 o'clock in Germany?
Yeah, it's 6 o'clock in Germany. For our side, they changed now the clock last weekend, so end of October. So now there's 2 hours difference between Iraq and Germany. So that's why we're saying here we start at 8 o'clock, and also when we need to go to office, etc. Yeah, it's not possible that we start earlier, sadly. But let's say we have here maybe we can finish at, like I said, somewhere at 5:30 or something, so that we getting there, or 5:15. We see how far we are. Yeah.
Okay, okay, Mr.
If this is big, but sadly I cannot change this at the moment. Yeah.
Yes, I understand. Thank you.
Okay. Then we make the break now, 15 minutes, and then we go on afterwards.
Okay.
Thank you.